Welcome to Simerics. The following is a demonstration of what the multi-phase module in the Simerics virtual testing code PumpLinks and Simerics MP is capable of. I will list some typical applications for which the multi-phase module is useful for modeling gas-liquid interface movement and the motion of the interfaces between any number of immiscible components that are included in the simulation. Some typical applications are pump priming, flow over weirs, tank sloshing, liquid ring pumps, crankcase lubrication, and gearbox splashing. I'll briefly list the relevant features and then explain them in more detail. The relevant features offered by Simerics MP and PumpLinks are the modeling of multi-phases, mass is conserved, indicating that physical laws are not violated, so there's no mass loss. Compressible and incompressible effects are accounted for. It contains implicit and explicit time algorithms. Sharp interfaces. The interface thickness is refined. And PumpLinks has surface tension, wall contact models, which take into account a more detailed behavior of the fluid. Let me elaborate on what these features accomplish. Multi-phases. Any number of immiscible components can be modeled, such as oil and water, water and air, air, water, and oil. No mass loss. All mass is conserved for all components, indicating that physical laws are obeyed. Compressible and incompressible. The software accounts for the compressibility of both liquid and gas phases. Implicit and explicit time algorithms. In addition to the explicit time algorithm, PumpLinks and Simerics MP offers an implicit time algorithm for shorter computing time. Sharp interfaces. Simerics MP and PumpLinks offers higher order surface reconstruction algorithms which result in sharp interfaces. Surface tension model. In many types of multi-phase flows, the surface tension plays an important role in the interface behavior. The multi-phase module takes this into account. The wall contact model. Since surface tension is accounted for, PumpLinks includes the contact angle between liquids and solid surfaces so that the phase interface is predicted properly. Here is a validation case of flow over a weir. You can see that the predicted shape of the free surface matches experimental data almost exactly. This is another validation case of a volume of water initially static but then released to flow under the influence of gravity. This is the dam breaking problem. We see a comparison of experimental visualization versus a PumpLinks simulation. The predicted free surface matches quite well to the photos of the experiment. This is a simulation of a mixing tank. It shows that complex geometry with multiple rotating blades was modeled using rotating and sliding meshes. It includes surface tension and the liquid mass is conserved. Here we have the classical tank sloshing problem. The liquid movement is driven by time-dependent accelerations on the container, simulating a box half full of liquid, which is moving. The liquid volume is conserved, surface tension is included, and the gas, which is air, is compressible, modeled using the ideal gas law. Here is a view where the liquid is transparent so that any internal free surface structures can be seen. Here is an automotive application, gearbox splashing. The gear teeth shape is preserved, micro-sized clearances are modeled. We use rotating, sliding, and deforming meshes, and again, liquid volume is conserved, and the air is compressible. At 150 RPM, we see that the liquid, which is oil, is scooped up by the gear teeth rather gently as gravity dominates the system. Here is another automotive application, pump self-priming. Often a pump and connected hardware is filled with air, and as the pumping operation begins, the air is displaced by the liquid entering the system from a reservoir. Pump links can model all types of pumps, including positive displacement pumps. The compressibility of the gas ensures that the suction pressure is predicted correctly. As always, the mass is conserved, which is equivalent to preserving volume for incompressible phases. All geometry details down to the micron scale are resolved. The effective forces due to tank motion are easily included, as well as viscous effects such as surface tension and contact angle. Here is a close-up of the pickup tube and of the fluid rotor interaction as the oil is successfully drawn into the pump and then expelled. In conclusion, let me summarize briefly. Recently, the Simerics virtual testing software has added a multiphase module which models the interfaces between any number of immiscible fluid types. Pump links can model a wide variety of flow fields characterized by complex geometries including micron-sized gaps, which can be modeled using any type of mesh, and it utilizes moving, sliding, and deforming mesh volume technology. All types of pumps, motors, compressors, and valves can be analyzed using pump links. Analysis of the full range of operation, including startup and shutdown, is handled with ease. The accuracy of the results is proven by the excellent agreement with experimental data. The convergence characteristics of pump links shows that the investigator is not required to manipulate solver settings to get a converged solution. The success of the default settings show the robust quality of the solver. Finally, due to the unmatched speed of pump links, analysis turnaround time allows for full 3D transient simulations to be performed routinely. Please feel free to contact us if you have any questions or would like information on related capabilities. If you'd like a demo of your device, please contact us and we'll make the necessary arrangements.